So 3 minutes after, I say, let's start. So welcome to this open software-defined vehicle of the future initiative community tech talk organized by the FEDERATE project. So today we have a great talk from the University of Oulu from SDVoF. I hope I pronounced it correctly. So it's about lessons learned from ROS, vehicle data extraction, and ELROP convoying scenarios with ROS data and OpenPilot. So I will, in the meanwhile, let people in which are still joining, and I will hand over to you. So if you can share your screen, and then we can start, let's say.
Sure. Yeah.
Yes.
Are you able to see the screen?
Yes.
Okay, great.
Yes.
Okay, to give a very short introduction about myself, I'm Siva Ariram. I'm a postdoctoral researcher here at the BISC Robotics, University of Oulu, Finland, and I have been working here for last more than 8 years, and I have different expertise in areas in autonomous perception and mobile robotic vision, and also semantic segmentation, and a few other areas as well. So here today, I'm here to present the title itself. It says that the lessons learned from ROS2, basically, which also includes the vehicle data extraction using ROS2 and also other tools, and few other like challenges that we have participated, which is LROB. It's a European land robot trial challenge where there are like convoying scenarios and how we have made it happen to that challenge with the ROS data and also other open source open pilot software. Yeah. So this is not the like kind of agenda for the presentation, but these are the topics that I will be included in. I'll be presented in today's presentation. So which itself says the LROP convoying scenario, which is a challenge, which I'll explain later what is the challenge about, and then the hardware layer that we have used in that challenge, and then what we were going through when we are working with ROS2 especially, and also the takeaways of ROS2, and also the another convoying scenario, which was another European level project called Fireman, where we had to use the mobile robot and autonomous vehicle for excavation. Yeah, and then there'll be a detailed presentation about open pilot message nodes, which we have used in these convoying scenarios. Yeah, so I can say that like altogether it may take maybe 30 to 35 minutes, I guess so. So after that we can have the question answer session. So yeah. So yeah, why basically I wanted to explain or give a presentation about this topic is that since we have had extensive experience in ROS2, and also the rise of distributed autonomous system, which is basically it can be multi-robot or multi-vehicle setups, and then there is also increasing need for interoperable tooling such as ROS2 along with any automotive frameworks like AutoWare, or there are many open source software which are available for the automotive frameworks. And yeah, why here the convoying is relevant, which is there are few challenges. Mainly, it focused completely on the logistics automation purpose, and also in the defense, where they expect the, like, let's say the heavy vehicles or the any robots that they're expecting to be move in a convoying or following one after the other, and obviously for other research purposes as well. And then in real world scenario, as I said, like there are few events that I have stated, which is LRO, the European Land Robotics Forum. In some of you might have already heard about this. So this happens like every 2 years once, and we do participate from, I think, 2014, if I'm correct, yeah. And then there is also the need of these sort of firefighter robots, especially which one of the project we were involved in called Fireman. So there we have developed something, some robots similar to this, where it can help to these firefighters, especially in the difficult terrains inside a forest fire and things like that. Yeah, so here is the team that it was, I think, back in 2022. So where we had participated in this LROP challenge, where the scenario was like there has to be one vehicle which has to follow the lead vehicle. So the lead vehicle is not necessarily to be autonomous, so it can be manually driven, but the following vehicle has to be autonomously following the lead vehicle. So, and the other requirement was like the complete automatic driving can be, it should not be less than 70%, like let's say. So, and then the terrain, which also contains, like as you see in the picture, like it's a non-urban and very constrained environment, since it was like for a defense purpose. So it was designed according to their needs. So there were like hilly terrain with roads and paths ranging from small streets as well. So where we had to do 2 successful laps of 3 kilometers each. So these are like some of the like defined protocol for the challenge. And it was back in Austria where we have participated in this challenge, and we have also participated in few other scenarios as well with our mobile robots, where you can see in this other picture down there. So in that event, so I would like to focus more on one scenario, which was this convoying scenario, where I was explaining about the following vehicle has to follow autonomously the lead vehicle. So where the focus was only at the ground level, since then we decided to dedicate our hardware layer at the bottom of the vehicle. It really doesn't impact according to that particular challenge. So it was like well fitted, I would say. And there is also another reason that we have fitted in this way. The complete sensor setup has been like portable, so which we can use it in other robots as well, which you have seen in that previous picture which I showed. So these are the sensors that we have used by then. So now it has been upgraded quite well. I mean, yeah, to the latest sensors, and here you can see the sensor architectures, like how the data flows and things like that. So basically, you can see this temporary file system where we also had this data storage option and stuff like that. So to go more in detail about how exactly that we have achieved this convoying challenge, which is like that's when we started working with the ROS2. So especially it was like, I think that's the year the ROS2 got introduced, and we had like plenty of experience previously with ROS, but we had like especially some problems with the communication level. So where we always like losing some communication in the important area where we have to handle this sort of real-time real world scenario in a different terrains, or like very very hilly terrains or something like that. So where we decided to work with ROS2 is like especially ROS2 was optimized to handle this high data rate with the LiDAR scans, or even with the, like, let's say, camera frames, where we have to use these camera frames for the mask RCNN, where we did the semantic segmentation to segment between different terrains, basically, and also other sensors like GPS, IMU, fusion streams, and also map and terrain data. So this allows all perception modules and segmentation outputs to integrate smoothly. When it comes to real-time synchronization, like especially synchronized odometry and also this data distribution service, which we call like DDS for communication, giving real-time capabilities and flexible quality of system, like the measurement QoS measurement settings were very much useful. And also that we have used this socket can, especially to publish these ROS2 publishes and subscribes to CAN related topics. So socket can ROS acts as the ROS2 drive or bridge, whatever we can call. And socket can is the is another advantage was like it had this Linux kernel interface handling the CAN frames directly. So all it was needed is like just the DBC file to decode the data that we received via CAN bus. So so this kind of also helped us to achieve this onboard CAN bus connects to various ECUs, allowing ROS2 to read and write vehicle signals, especially. Yeah. So moving on this to this convoying scenario is basically, as I said, like one car follows another car. We have done this in real-time semantic segmentation, where the goal is to classify each pixel into this original images that you see in the bottom into fixed set of categories without differentiating the object instance, I call. So here you see the segmented frames in real time, some of the sample frames that I have given. So here, at least, since there was no like, let's say, it was like very constrained or defined environment. So since then, like, you can see very much static obstacles than the dynamic ones. So which we didn't really face any issue, and we were able to achieve 2 successful laps in I think very less time than the other competitors. Yeah, sorry. I noticed that someone was raising the hand. Yeah, can we have the question answer at the late, or I don't know, whatever is better.
Yeah, I'm not sure. Yeah, can I give question now, or should I give the question at the end?
You can ask now. It's fine.
Yeah, I want to ask just a little bit a technical thing in the previous slide. Can you go back one slide? I'm interested in the part that socket can. Yeah, the socket can. So how did you connect the CAN bus of the car to your system over ODB2, or you have specific interface?
Yeah, it was OBD2, but since like we had this RAV4, it had like some issue with this DBC file, where we have to decode the data that we receive via this OBD port. So for that, we had to just sneak into some other like software, and we had to contact the Toyota provider here in Finland, and even they couldn't able to help, but we got it, at least we got the data decoded what we what we needed in this application. But though we couldn't able to fully decode the data because we didn't find the latest DBC file for this particular vehicle model. Yeah.
Yeah, I see. Yeah, thanks.
Thank you. So yes, so from this convoying scenario, that what we have achieved is like basically where we are able to localize the vehicle properly, since like it was very predefined environment, so there was no such difficulties in localizing, or like even in the perception related tasks, we really didn't had any issue with except few unexpected breakings were there, and then few smaller turns were there, like two where we had to pass through. And then yeah, we achieved third place in this convoying scenario overall. So the main reason was like that we were the I think only one who could able to achieve these 2 successful laps, and which also exceeds 70% of autonomous driving, and faster as well. So one thing that we were like lack of was that this especially safety when it comes to this real-time constraints. So which was not there, except the safety, like we were supposed to implement this emergency stop button inside the vehicle, but it was not there. It needs to be mechanically installed. So this was like one of the constraints that we had to we achieved this third place. Otherwise, we could have done it better, I would say. And yeah, so overall, from this ROS2 takeaways, especially from this L-road convoying scenario, I would say this first. I want to highlight the most important ROS2 specific lessons that we have learned during the L-road. So first one, which you see that ROS2 proved that extremely capable of handling this high bandwidth sensor data, especially where we were running this LiDAR and then semantic segmentation on the camera data and GNSS IMU simultaneously inside a let's say kind of forest environment, or like a very different terrains. And ROS2 also handled the streaming and synchronization reliably when compared to the ROS1, the previous version. So this was critical for real-time convoying. So and then the another major takeaway was the importance of this QoS tuning, especially where we also kind of the wireless communication in that L-rope was not so stable, like trees and hills, and then long distances especially created these dropouts. So ROS2's DDS and QoS profiles allowed us to choose the right reliability and history settings to keep communication stable between the vehicles, especially not only the vehicles, also to the control station, like where we had like let's say 1 kilometer away at least. Yeah. And then with the namespaces and modular node architecture, so we're also very valuable. Each vehicle in the convoy had its own namespace, which made this this coordination very well, like clean and scalable as well. And then the another key strength which we see, it was like how easily the ROS2 allowed us to integrate the mask RCN and segmentation output, which we could plug into the segmentation node and publish the results and immediately feed them into the tracking and planning nodes without rewriting the whole system. So that was very, very big advantage, I would say. And also the another thing was the timing and determinism also mattered a lot, as you see. So with the tight curves, as I mentioned, the path in that path, we had to handle the tight curves and inclines and rough terrains. The convoy needed predictable processing loops, where the ROS2s are able to execute the model and gave us stable callback timing, which directly improved follower vehicle behavior. We also relied heavily on the socket CAN integration, especially to communicate with the vehicle ECUs. So ROS2 could publish and subscribe to CAN topics seamlessly and directly to it had this publisher with a socket CAN, so which gave us reliable low-level control signals during the convoy. So overall, I could say that this challenge showed us the ROS2 is not just an middleware. So it can be robust in many cases and absolutely suitable for real world or multi-vehicle autonomous driving scenarios as well. So yeah, moving on to the to Fireman project that we demonstrated during, I think, 2024 summer, if I'm correct. So this is the project like where funded by Academy of Finland, and we have demonstrated where the wildfire sites are often not easy to reach. So we had this fire school academy, how do you call it, like here located in Kuopio in Finland. So where we had to demonstrate this convoying scenario, where the scenario is like pretty much same. At least the terrains were pretty much same than that what we have faced in LROB, but but again, the sites can be remote, their terrain can be difficult to navigate. As part of the Fireman project, this automatic logistics robot that you see in here has been tested, and that can travel even in difficult terrain. So which is another reason that we want to replace this lead vehicle which we had in the LROB scenario with this robot, where this robot has a impressive payload capacity of carrying up to 800 kilos. So this was also like completely designed. And as I said, the sensor module which you see in here, which was like meant to be portable, and we can straight away move that and fit into any of the mobile robot or into the car, and make the robot autonomously moving, and yeah, things like that. So that was also another purpose in this scenario, that where we were able to achieve both the vehicles can be driven autonomously. And yeah. So yeah, in this convoying scenario where we have had given a thought about using of OpenPilot, where this open source software to control the following vehicle especially. So where we really didn't have to process, like, let's say, other or like high-end information, or like from the sensors like LiDAR or high processing sensors. So which we moved everything to this following, lead robotic vehicle, which you see in the picture. So which could take care of all the other, like, for example, obstacle avoidance and autonomous path planning. Such things was taken care by this lead robot. So only thing this following vehicle has to do is just simply track this robot, detect and track this robot, and follow the similar path of that robot autonomously. So that is what we had the plan. And so for that is another reason that we chose to go with the OpenPilot, where this rate monitoring, which was able to detect and log when control loops miss deadlines. So where we were also able to overcome this safety constraints which we had in that LROB, and also this degradation, I would say that, like, disabling this autonomy if timing constraints are not met. So that was one other advantage which we had in this OpenPilot. software. And also safety in terms of hardware, that so this open pilot basically have this panda which enforces kind of watchdog timeouts if the commands stop. So then steering torque goes to 0 automatically. So that was like one big that we could able to achieve it just by having one simple laptop, I would say. So in these pictures that you see that how we have done this calibration process, and then how we have achieved this like tracking of this lead robotic vehicle, which you see in the front of the car. And then so there was also like nodes under this open pilot where particular dedicated nodes for planning and then tracking and stuff like that, which you will see in the later slides. So yeah, as I said, like these are the open pilot messages that message nodes that we have been worked, especially in this scenario, which I have mentioned. So first thing, it was like it has to go through here. This is only from the perspective of the following vehicle, where it only had to have just a simple camera and its vision. So where there was this vision D node under this open pilot message, which was responsible for the camera input, and also this also helps to compress the image while processing, and the vision IPC, which is responsible to of sending frames to the vision model that you see here in this node tracking. So this was the first step that we in the entire architecture that you see. And then the next one was like we decided to use the same mask RCNN, which replaces or extends the model input output, model D message input output, I would say. So we could have also gone into a simple object detection, but then like since we have already had trained our own model in this mask RCNN for different applications. So, and we also had this additional terrain segmentations as well, which it was not needed in this scenario, but still that is another reason that it was like easily like developed into to this application as well, I would say. So this model D, basically it was responsible for tracking and prediction. So as I said, so this open pilot itself had this by default, but this tracking was like very minimal, and then like even this prediction which can gives like lane lines and path predictions, but where we had to run this scenario where there were like not really a proper road or a path or dedicated gravel road or something. So it was more rough terrains which we had. Yeah. So this is another message, the third one that we used in this architecture, which is like planner D, where this was helpful for like lane centering, and also in this open pilot software where this adaptive cruise will set the minimum speed of 30 kilometers per hour, but we had to bring that down to set the maximum of 30 kilometers per hour because of the safety reasons. And we didn't want to because the vehicle was also not completely SUV, so we didn't want to ruin it. So that is another reason we kept the maximum speed of 30 kilometers per hour. And the next following steps in this architecture is like the controls T, where it was helpful to generate the steering and throttle and also the brake targets. So, and it could be able to publish this actuator commands where we didn't had to install any additional actuators, which means like we didn't had to design a mechanical actuators to control the vehicle. And also it consumes this plan and model v2 nodes as well. And then the CAN message is another thing that this OpenPilot had this integrated Panda, a small device which we had to buy, so which was responsible, like especially this board D message, which handles the CAN input output through this Panda, so which had this hardware safety. It can be called as like hardware safety gatekeeper for the CAN bus, I would say, yeah, and responsible for vehicle control CAN and radar CAN and also the powertrain CAN, yeah. Yeah, before moving to the conclusion, I would like to show the video. Yeah.
Are you aware that there's no sound?
Sorry?
There's no sound.
Yes. There is just a music,
sound.
but yes, it's a,
Okay,
it doesn't have, it just has a music. But yeah, I can explain.
Yeah, okay.
So this is basically just to show when we did this real-time demonstration, and there is a person sitting in there, like just to show that it can take the payload, and it has been also tested by having like somewhere 9 to 10 people. We are sitting on it and yeah, driving around. And it also had like capability of pulling additional payload, like which has this trailer in it. You see that which can take another.
So the car is here automatically following your robot.
Yes. Yes. It's actually both are autonomously driving. So even the robot is completely autonomous, and yeah. But here we wanted to highlight just the following, autonomous following.
Yeah, and of course we have the safety drivers in the real Toyota, because that's what the local traffic authority requires us to do.
Yes. So since like we didn't had this the emergency stop button, that the safety drivers has to be there and seated on the driver's seat. So it was like kind of a mandatory. And so that was the video. And moving to the conclusion and like some recommendations like towards these topics. So which we have identified is, like, as I said, ROS2 is powerful but demands very careful configurations, especially with this QoS and timing. So it also gives like very clean data pipelines, which are essential for any sort of autonomous applications, I would say. So in terms of this data pipelines, it is far better than the ROS1. And the OpenPilot can produce also a flexible research platform, but now I think after 2024 they have stopped supporting this to this, like to modify the external vehicle, I guess. So at least the support has been stopped from their side, but still there are like still there are the open source software is available, and also the libraries are available for many vehicles, but it may not be updated. And then the recommendations are like, maybe it's a good idea to move towards this ROS2 Galactic plus this QoS tuning templates, and also standardize these data extraction interfaces. And another thing could be like simulator to real-time testing, where the framework for convoying could be developed. Yeah. And then, yeah, here is the future work from our research group, especially. So where we have purchased this autonomous electric, just an electric van. So our motive is to make this autonomous driving in constrained airfield environment. So, but because that is what the project requires. The project name, it's called SARC, and it's Sustainable and Advanced Aviation Consortium. So with this link, you can see what exactly this project is about. So where we also have plans to use this vehicle to inspect the runway for e-flight, basically. So electric flight. So to detect any sort of foreign object debris and cracks, and also ice and snow accumulation on the runway, and in a remote area, I would say. And then also we are like focusing towards this visual plus wheel-based surface assessment, basically by using the camera streams with wheel-based sensors, and like IME encoders, or like vibration based on, or the deceleration and stuff like that. Yeah. And then we also have plans to make this autonomous utility vehicles for electric aviation support. Basically, it could act as a battery unit mover for electric flight, where it could be an autonomous battery mover. And also, the another thing was like to act as a e-flight maintenance requirement vehicle. So, which means a dedicated autonomous vehicle carrying like, let's say, diagnostic tools and spares can synchronize with electric aircraft turnaround cycles, and also to maintain this log maintenance digitally. It could be beneficial. Yeah. So yeah, that's it. Thank you, everyone. Thank you for attending this and listening to this presentation, and feel free to ask questions. Yeah. Yes.
Yeah.
Thank you very much. I see the first hand raised. Please, ma'am. So
yeah, you can go first. Yeah.
No, it's on your side. So please ask.
Okay. Yeah. I just have a question for the slide. I have two questions. So the first one, I see you use the ROS2 Galactic. So I want to ask about the DDS implementation. Which one have you used? Like the ROS middleware, which one have you used for the system?
Sorry for the wrong understanding. So we haven't used the ROS2 Galactic, but so that was like kind of a recommendation towards like that we move towards ROS2 Galactic in future. Yeah.
You moving to ROS2. So I see you using the
ROS we will be
your system.
Yes.
So which one have you used in your system? Which ROS version?
Yeah, it was.
Because yeah, can you go back? I think the slide for the technical slide, I think where you describe your system flow.
Yes.
I see you, for example, the socket can, you use the ROS2 in there. Yeah, for example, this part.
Yeah, in here we didn't use the ROS2 at all. Yeah.
Yeah, before this one. Yeah.
So in here.
Yeah.
Right. So yeah, it was ROS2 Foxy.
ROS2 Foxy, and which middleware which middleware you use in here, like eProxima or Open or Fast or Open DDS, or I mean, which middleware in here we use?
It was OpenDDS.
OpenDDS.
Yeah.
Okay. Okay, good. My second question is about the Open Pilot. In here, I have a little bit confused. So, is it the ROS2 and the Open Pilot come together, or in here you try to introduce two different systems?
No, here like we just two different system, and here like we completely got rid of ROS2, and the whatever the ROS2 that I was explaining about, it was completely running on the lead robotic vehicle, as you see in the picture. So for example, you see the sensor setup in this lead robotic vehicle in front. So it was whatever I was showing in this LROP scenario, which was completely running in this robot, and then with the car, so we just had to depend only on the Open Pilot.
So one question about Open Pilot: are you running it on a computer or you run on a Comma AI device?
Yeah, by then it was in a computer, but they stopped this computer support, I think, after 2024, if I'm correct. Yeah, but it was in computer. And we can work with the computer, and we can let's say modify everything, and we can push it to the device Comma AI. Yeah.
I see. Because I see in your picture you have the left one is the Comma AI device, right?
Yeah. Yes.
And then you have a computer as well. So
yeah, on the right side. So by then there was a possibility. So now I think there is no at least like very limited options working with the computer, if I'm correct.
I see.
In recent years, I haven't really looked into this Open Pilot. Yeah.
So the following of the car it rely on the Comma AI device.
Yes. Following up the lead robotic vehicle, I would say.
I see. So how you define the following in here in the Open Pilot? How you define it?
So here, as I showed, like we used this mask RCNN to identify to detect the targeted object. So which we have also implemented in the LROP convoying scenario. So where we kind of done the detection and tracking. Sorry.
Where is one running? Is it run on the Comma AI device or run on your computer?
On the computer. On the computer.
I see.
Yeah.
Then how it communicate? Interesting in how your computer communicate with the Comma AI device for control the car.
So that's what like so we were able to achieve like pushing this to like so whatever the version that you work with the laptop, so it can be pushed to the Comma AI device by then. So it was with the I think name called Echo, if I'm correct. Now it has been stopped as well, the Comma AI Echo. So it is not like a Comma AI 2 or Comma AI 1. So it was, or sorry if I'm wrong with the name, but it was Comma AI Echo or Aeon, sorry, EON.
So yeah. I mean, is it wirelessly communicate or it wire?
No. So we had to run the model and push it to the Comma Aeon. So once it is like kind of programmed, then it cannot be touched at all. So it is not like kind of wireless. So once we program and put it in the car and connect the Comma Aeon to the car using the OBD, as usual, like how we do, and then we kind of like had this activate like either a normal mode of how Comma AI works or like what we require for these particular tasks. So we could able to like, for example, shut off all the unnecessary nodes that we didn't want to in this application. Yeah, but it was not like wirelessly communicated or something like that. No.
I see. The last question: is this one open source?
Yes.
Can you share the repo? Maybe we want to try to implement re-implement this?
Yeah, sure. But as I said, like I can share, but as I said, like that there is no more support with the computer, especially with the Open Pilot. But still, yeah, you can try out. Sure.
Yeah. Thanks.
Thank you.
Yeah.
Then Alexandru raised his hand.
Hello. Thank you. So yeah, I have a couple of questions also. I would start based on this picture. Can you tell me again how the nodes themselves are split between the two devices? And yeah, on the laptop, at least I saw Linux that you used, but considering real-time requirements and something like that, have you used real-time OS, or do you think a real-time OS would be needed for this type of scenarios?
No, especially with the Open Pilot, like the real-time OS was not really needed. It was just the Linux. So that was at least that is what they were supporting with the Open Pilot open source, especially with the laptop. So it was not really necessary to have the real-time operating system to handle this. Yeah.
Mm-hmm. And the 4 nodes, how were split in each device? So the majority of them were running on the laptop, or
yeah, everything is running on the laptop.
Okay, understood. Mm-hmm.
Yeah,
I'm thinking if
and via
I'm
Panda,
not sure, but
it could, yeah, the Panda could is the responsible for communicating between the laptop and then the car or the
When you say Open Pilot has support for Linux, is there a limitation in the architecture? Because, for example, in automotive domain right now, we have these very smart socks that really run Linux for ARMv8 or ARMv8.2 architectures. And I'm thinking if this could be ported at some point on running in such a system on chip that really has enough resources to run something like this.
Yeah.
Or maybe this could be a next step. I don't know.
I think when the Open Pilot is run either partly or fully on a laptop, like instead of the dedicated Kama hardware. So I think that was kind of one of the major issue that they have faced to like let's say this safety model breaks without Panda and things like that. So I think that is another reason they completely stopped supporting this working with the like Open Pilot working with the PC, I guess. So by then at least there was no big limitations maybe to drive it on road. So there were like many complications like accurate lane following and things like that. For example, it will like the moment you connect with a laptop and which has like Open Pilot to control the car, so it will deactivate this how can I say, I don't know, this sudden brake or like autonomous braking option that this latest vehicle have, so which will be disabled, which was disabled by then. So these sort of things was not really good. So maybe yeah, I believe that could be also one of the reasons that they stopped completely supporting.
Okay. Yeah. Understood. Then maybe going to the next question that I have about the structure of the data between DDS and these CAN sockets. You said that at some point in the presentation that somehow you structured the data in the same way between those two technologies and physical layers. And I'm curious, how did you really structure the data? Did you had topics, or how data was compatible flowing from one physical layer to the other, or being structured and centralized from two different, from DDS, which is Ethernet, and CAN, which is, each of them come with some limitations, and you need to be careful, especially when structuring data from two physical layers together.
Yes. So yeah, we, as I said, like especially with this socket CAN, so it also had like support with ROS2 like libraries. So where like this DDS is the middleware layer used by ROS2 for the internode communication. So this socket can like there was like option kind of that we have created a ROS2 CAN node, and under that there will be socket CAN ROS, which we have created. So and then under that socket CAN ROS, so that will handle whatever that we are getting the message from through the socket CAN interface. So that's how we.
But considering that in ROS2 you have data stored as topics, I assume this was the same type of abstraction.
Yes, similarly,
here.
Yes. Yeah.
Okay, and my last question would be, considering the DDS QoS, are you aware of what policies did you use, or what was the most important one? Because at some point you spoke about determinism and maybe some real-time behavior, limited but at least deterministic. And I'm curious if you are aware of what QoS policies from DDS were the most important in this type of implementation.
At least like when we were using the ROS1, so we could able to see like lot of like loss of messages, and we really couldn't measure extensively about this QoS, like QoS definition, like how data is delivered and not just what data is sent and things like that. But at least we saw that it was working better within, like, let's say 3 kilometers of range. Of course, like we had to set the wireless transmitter and receiver like bit higher and stuff like that with the practicalities, but we couldn't really able to provide the communication foundation in ROS2.
I'm thinking
the detail we didn't able to measure, but we were able to see the quite drastic difference between ROS and ROS2.
The idea is that at least in ROS2, where DDS is the middleware, DDS has a couple of policies of handling data according to the use cases. And here, for example, I assume that you also have data that you cannot really miss, and you need to be reliable. And that's the policy that's really for this type of scenarios where you really don't need to miss any information from a sensor or from camera or whatever. And also there is other policies that are more oriented to performance or to closer to real-time delivery of the data, which I assume also could be somehow mapped in this architecture. And yeah, considering this, there's a huge amount of data and coming in different rhythms from different nodes and flowing in different directions. I was curious exactly if you really tune the QoS in such a way that you could maximize the efficiency of how the data flows.
So in ROS1, as you said, like it didn't had any sort of this dedicated data distribution service or something where we had to use this custom TCP UDP based, I guess. So which was not designed for like real time distributed or like, let's say, multi-robot communication systems and stuff like that. So I think which itself in ROS2, it was like fully decentralized and no ROS master, I guess. So that was a huge difference I see between ROS1 and ROS2. Yeah.
Okay. Thank you for the answers. And
thank you
congratulations.
So much.
It's really a nice project, and I see it very useful even in industry and public services and so on. So good job and congrats.
Sure. Thank you so much.
So, additional questions from the audience? So there's some discussion ongoing in the chat about ROS versions and long-term support versions. And
I have a question. on the slide earlier, you talked about degradation. Could you maybe go into that? What kind of
sorry,
degradation did you?
Okay. I think it was
one of the earliest ones. I think second or third slide. Yeah, there it was. Next and next one. No, that before.
So sorry. You mean this way or okay?
It was. It
Is
had
it here?
three. Wait, I look up the number.
Okay, yeah, it's a open pilot.
This one
degradation.
exactly. Okay. This is just a.
Yeah, this is
something
just
that
to like
OpenPilot can do.
Yes. So disabling this autonomy function if the timing constraints are not met, something like that. Yeah.
Okay. Yeah.
Yeah. Any more questions?
Is this discussion about the ROS versions fine so far? I think that was then solved between them. So there are also some links shared about publications. So thanks for that. Are there additional questions or?
By the way, the question about this presentation itself, is it rely on any publication of use or it's just your presentation for today?
There are like few, like let's say at least the thesis publication, which I think Ella has shared now in the comments in the chat. But other than that, like yeah, there is no dedicated publication. But at least with this one, the fireman convoying scenario, there will be a publication soon.
Soon. Okay.
Yeah.
I see.
Because with the other airdrop convoying scenario, like we had some like let's say kind of not like restrictions, but where we are not allowed to publish like too much of technical information or about the event or something like that was there. Yeah, back then. But we have like we have another publication like where we talk about extensively about the ROS1, how we have used in a mobile robot, for example, for the same airdrop scenarios, like as you see in this picture, these land robots. So where we have implemented some sort of fire detection, like things like that. Yeah. I can share all the articles along with this presentation.
Then I think Ahmed has raised his hand.
Yeah, Ahmed.
Yes, thanks for the presentation. Very good project and nicely presented. Just curious about the effort breakdown. Do you think most of the effort goes into the software development, integration, or the field testing and trying out things in the physical world and things like that? So just curious, where what do you see most of the effort and the most important tasks?
Yeah, I would say like, yeah, in two different scenarios, like two different cases. So for example, in this LRO where like it was like equal effort from both hardware and software side, where we had to integrate this LiDAR and other high-level sensors into the system. But in that other one, yeah, in this scenario, like where it was more focused on the software side, so it was like, I would say 80% of efforts towards software side in this fireman convoying scenario, where we had to focus only on the open pilot, open source software. And yeah, we in this bottom picture that you see, it's a test track which is called Oluzone. So it's a race track basically here in our municipality. So that is where like we do all our tests, autonomy tests, and we do have like different types of race tracks like gravel roads and different terrains like that around there. So that is where we perform our tests.
Thank you.
Yeah, thank you.
Yes, got the message. Thanks.
Additional questions? If not, then I say thank you very much for this impressive presentation. Can you share also the slide with us here in the chat?
Yeah, sure.
Okay.
Maybe yeah, I can convert the PDF and can I share it to you, Mario? In some time?
Also fine. Yeah.
Yes.
Fine for me.
Sure.
Okay, so if there are no more questions, then I say thank you again for this great presentation. Thank you for the audience for joining. This was interesting for you, and yeah, hopefully we hear us at the next TechTalk. So there is one planned with the Open Hardware Foundation. They gave us some insights about their work, about RISC-V development. Also something about ecosystem mobility. We got a presentation, and also with the Autoware guys, there's a presentation planned at the beginning of June, I think, where they gave us an introduction about that. Okay, so then I say thank you to every one of you, and hear us and see you. Thank you. Bye.
Thank you. Thank you so
Thank
much.
you.
Bye.
Thanks, Mario.
Thank you.
Bye.
Thank you. Bye bye.
Thank you.
Bye bye.
Thank you.